Okay, so these are the notes for 3.5, and 3.5 has a lot of unique characteristics that are worth looking at. Again, we want to be able to find all the zeros, and some of this information you have to remember can be outdated by using a graphing calculator. But we're still going to look at it, explore it a little bit, see some interesting things that happen. You won't use all of it as part of your homework, but it is worth investigating and seeing some interesting coincidences. For mathematicians, even 50 years ago, these were resources that were extremely important. What we're going to do is we're going to say, for instance, if we had a polynomial, and doing something like this, okay, a little cubic, and we wanted to kind of have an idea of where the zeros lived. We could build that set of options, the P over Q set, which we've done, or we want to know other ways to look, and what other ways can we narrow it down? One of the ways is to find points that are all the way on the right and all the way on the left, and we could sort of work our way in. And there's rules about what happens in synthetic division as long as we stay on the left and on the right if we have a negative and a positive result. Okay, so when the number we're going to divide by is positive, this is important. So I'm going to come over here to the next slide, and I'm going to show this is positive for the equation. Watch what happens when we go through the synthetic division. 2 times 2 is 4. 11 and 4 is 15. 2 times 15 is 30. Negative 7 and 30 is 21. 2 times 21, 23. That's my fault. 2 times 23 is 46, and negative 6, 46 is 40. Now this is not a 0. We know that 2 is not a 0. However, if 2 were to exist right here, because all of the numbers on the bottom row are positive the whole way across, we know that 2 is on the right of every 0 from this equation. Okay? Whatever happens, we know 2 is on the very far right. Maybe 1 would work, and we could try 1. Maybe 2 is, maybe the next value that is a 0 would be 1.5, but we know that 2 is on the right of all of the zeros. Now we're going to test to see if negative 7 is on the left. We have to use a negative for this left side deal. And so we're going to use our negative, and if we put the 2, that's negative 14, becomes negative 3, that becomes 21, that becomes 14, becomes negative 98, and that's negative 104. Okay, and so if we look at these, we notice it goes plus, negative, plus, negative. We see the sign switch every time. Well, when that happens, you're using a negative number, and that happens, the alternating signs, then you know that that is on the left of all the zeros. In fact, we find out that if we actually just slide into negative 6, we could actually show that that's one of the zeros. But we know that all of the zeros have to be either greater than negative 7 or less than 2. It's in that window. Okay, so it's called the upper and lower bound test. Again, if you had a graphing calculator and you just look at the graphing calculator, you might be able to find the zeros pretty quickly and tell where they are. However, if it's a bigger equation, okay, and the 0 exists at 12 or negative 13, you wouldn't see it on a traditional graph, and so you would have to zoom out or change your viewing window, or you would think that they didn't exist. And so for us, we want to be able to stretch out, maybe potentially by doing this upper and lower bound method. We have what's called the intermediate value theorem, okay, and it's used to approximate values of zeros. And really what it looks for is it says we want to show that a 0 must occur between two values. If I graph this equation on the graph, we're going to find that between 2 and 3, the equation is either going up or down, and that there's an intersection right here. The way we do that is by plugging in both values. When I put 2 in, when I put 3 in, if I put 2 here, 2 cubed is 8, minus 2 times 4, 2 times 2 is 4, minus 5. 8 minus 4 minus 5 is negative 1. So f of 2 is negative 1. So at 2, I should be down here at negative 1. Okay. Now I want to know what happens at 3. Well, if I put 3 in, 3 squared is 27. Minus 2 times 3 is 6. So minus 6 minus 5. We get 27 minus 6 is 21. Minus 5 is 16. And so I put 16. And obviously that's going to be way up here. But in order for me to get from here to there, from a negative number to a positive number, I'm going to have to cross through the x-axis somewhere. And so we have validated this idea that there must be a 0 between 2 and 3. What it is? Well, we could build the P over Q set. We could do a lot of different things. This is just about how else can we narrow down our search. Okay, so because this was negative and it became positive, or if it's positive and becomes negative, we know that there must have been a crossing of the x-axis. So a sign switch between two numbers means that there must be a crossing. Fundamental theorem of algebra, we've talked about this before. The exponent, the highest exponent, which is the degree of the polynomial, tells us how many solutions or roots that something will have. The issue is what happens when they're complex or imaginary values. How do we find those? This is one where if we actually graph this equation to try and find our zeros, it looks like this. We never actually see where it touches the x-axis because it doesn't. The only answers to these 4 roots are imaginary. And so how would we go about digging those out? Well, it's actually a little bit easier with this question. Or no, this isn't just imaginary. We would see some, sorry, let me back that up. I'm thinking of the wrong one. We would see them, but they're not whole numbers. It's somewhere between 2 and 3, okay? Sorry, so scratch this thing up here. Pretend that's not there. Between 2 and 3 and between negative 2 and negative 3, there are these solutions. Now, what are they, you know, and those kinds of things? It's actually kind of hard to tell. So what we're going to do is we're going to try factoring, but instead of using x to the 4th, we're going to do x squared and x squared, because that would give us our x to the 4th. The 28, how does it split? So we can subtract to 3. If we use 4 and 7, they have a difference of 3, so 4 and 7. So I'm going to go ahead and I'm going to make a negative 7 a positive 4. Now I want to know what makes this 0. Now this is factored completely because what do I do? How would I ever, I can't do a sum of squares, and this is a difference of squares, but the 7 doesn't have a square root. So what we're going to do is we're going to take each of these, x squared plus 4, and let it be 0, and x squared minus 7, and let it be 0. If we minus 4 from both sides, if we add 7, we get x squared equals 7, and over here x squared equals negative 4. To get rid of the square, we're going to take a square root, and when we take a square root, we have to put a plus or minus in front. So over here we get x equals plus or minus. Well, the square root of 4 is 2, but because of the negative, it's I. So those would never have shown up. We were looking for 4 roots, but we only saw 2 in the graph if you were to graph it. The other 2 are imaginary, so that's where those come from. Over here, x will equal plus or minus. 7 doesn't have a root and it doesn't break down, so we'll just do the square root of 7. You might say, Mr. Welch, did we really get our 4 answers? The answer is yes. We got plus or minus 7 and plus or minus 2i. If you take the square root of 7, you're going to get a number between 2 and 3, which makes sense given the picture we were talking about. The last thing we want to talk about is how do you write a polynomial with certain zeros if you know what degree it should be. So the first thing I want to do, I actually want to pretend this isn't here. I should have erased that, sorry. The first thing we want to do is recognize that it is a third degree. That means I'm going to have y equals a and then 3 parentheses. And I want to write an x in each of these in a way that gives me the right zeros. So if negative 3 is a 0, that means I have to have plus 3, because that would make that 0. Then I have this I. I'm being told that I is a 0, which would mean I need x minus I. The deal, though, one of the rules is that whenever you get an imaginary solution, you have to have its partner. If you get positive I, you have to have negative I. You have to have its partner. So that would make plus I. So this is an equation that I can now work with, and I can kind of come back over here and erase what I colored over. So here's my equation now. The problem is, I know that when I plug 1 in, I'm hoping to get 8. But I don't know what this number here is. If over here I get 4, then I need a 2 for A. If over here I get 8, I want 1 for A. And so it really depends on what I'm going to get out of this equation. Also, I don't like having these i's here. So can we FOIL this out to make it a little bit easier? That becomes x squared minus xi plus xi and minus I squared. Now I squared is a -1. So this really becomes x squared. These guys cancel. And minus a -1 is really +1. And then I have my x plus 3 and my a equals y. Well, now if I put in 1 for x, which is what this equation tells me to do, I should get 8 for y. So 8 equals a times 1 plus 3 times 1 squared plus 1. 1 plus 3 is 4. 1 plus 1 is 2. 4 times 2 is 8. So 8 equals a times 8. A would equal 1. So I can just come up here and stick a 1 here, or I could just erase the a and I would have my equation. Or what would be preferred is this version of the equation. I'd start with f of x equals 1, you could leave it empty, x plus 3 times x squared plus 1. We really don't like to have imaginary numbers in the middle of a polynomial. Okay? We'd like to hide them, if you will. Hopefully that's enough to get you through, and we'll see you in class. Good luck.